back to chemistry. Today is one of my absolute favorite lessons because I'm going to show you a trick I haven't seen anywhere else for determining where groups are going to go when you're performing EAS. I'm going to show you that first, and then we're going to talk about Friedel-Crafts Alkylation in more detail, and then do an example problem to wrap up. Let's get started. Here, I've got a donating group on benzene. If you don't remember exactly the difference between a donating or withdrawing group, or why an alkyl group in this case is a donating group, you can review my Birch reduction video for more information. So here when we have a donating group, a lot of us remember that when we perform EAS, we get, well, an ortho-para distribution. We get an ortho product and a para product. In this case, I added on an atom of chlorine. All right. How do we remember it's ortho? Well, you can actually see the shape of the O right here between the two groups that are on the benzene ring, making an O for ortho, and then we can see this P formed here for para. And that's a really neat way of remembering. Of course, we have a trick just like that for meta. So if we look at a withdrawing group here, we're going to say withdrawers direct meta. So where's that M hiding? Here it is, and as we turn the molecule to the side, we can really see that M shape emerge between the two groups on the benzene ring. It's really easy to remember. So in general, we see that donors direct ortho-para and withdrawers direct meta. Let's look at another example to see if this holds. All right, on the top here, I've got this ether oxygen, which is a great donor, and it directs ortho-para. On the bottom, I've got chlorine, which is a halogen, is a slight withdrawer, so it'll direct Wait, what? It directs ortho-para? There's got to be something else going on here. Well, look at the chlorine and the oxygen. They both have lone pairs, and their atoms directly bonded to the benzene ring. Well, it turns out that's pretty important. In fact, those lone pairs, when we're performing EAS, actually enable a fourth resonance structure in one of the intermediates if we direct ortho-para. If we direct meta, we don't get as many resonance structures in that intermediate. So the presence of the lone pairs directs ortho-para because we can get extra resonance structures that way. And that directorship effect, that stabilizing effect on the intermediate, outweighs the withdrawing effect of the chlorine. So we've got to have a way to resolve this, right? I mean, there's so many rules to remember. So I've come up with a neat little trick here that'll help you remember what directs where. All right, sometimes you just got to turn things on their head and look at things upside down or from a different perspective to really understand them, so pay attention very closely. Let's look at the word withdrawers. Well, here, when we look at it from a different perspective, we see withdrawers direct meta. Do you see how the W became an M? Well, let's look at the word donors now. Well, donors direct ortho-para. Now, what about the lone pairs and remembering how the presence of the lone pairs direct ortho-para? There's the lone pair right there, hiding in the O and P. So, withdrawers direct meta, donors direct ortho-para, but if you've got a lone pair on that atom directly bonded to the benzene ring, you're going to direct ortho-para. Now let's take a look at Friedel-Crafts Alkylation. Here I have benzene. I'm going to treat it with the alkyl chloride as shown and AlCl3, which is necessary for Friedel-Crafts. Well, first thing is that the chlorine from the alkyl chloride interacts with the AlCl3. And in a concerted step here, we get a hydride shift to a rearrangement with this AlCl4 group leaving. I think that's a little complicated, at least when we're trying to predict products. So although this isn't chemically exactly what happens, I like to look at it as if you just have the AlCl4 group or the original chlorine from the molecule dropping off, leaving you with a carbocation. In this case, we know that primary carbocations don't form, so we're going to need to rearrange. Well, what's better than a primary? A tertiary for sure, and we can accomplish that with a hydride shift. So if we do that, we end up with our tertiary carbocation. Then what happens after that is then benzene is going to open up and grab this positive center, adding the group onto benzene. And then all that has to happen after this is that hydrogen is shown gets eliminated, and we restore aromaticity, and that is Friedel-Crafts alkylation. So, to summarize, determine if the first atom of the group directly bonded to the benzene ring has a lone pair. Well, if it does, we're going to direct ortho-para. If it doesn't, look at the group as a whole and determine if it's an electron withdrawing group or an electron donating group. Withdrawers direct meta, and donors direct ortho-para. If you don't remember exactly how to determine if a group is a withdrawer or a donor, see my Birch reduction video for more information. Then if you're performing Friedel-Crafts alkylation, remember to look for rearrangements. If you're performing acylation, you don't need to. That being said, let's do an example. I'm going to take our molecule on the left here containing a benzene ring, treat it with the alkyl chloride as shown in the presence of AlCl3. So first we want to see, is there a lone pair on the atom of the group directly bonded to the benzene ring? Well, no, of course there's not. So we'll move on to our next criteria. Is the group a withdrawing group or a donating group? Well, we know that alkyl groups are electron donors, and so this is an electron donating group, and thus it's going to direct ortho-para for the product. Speaking of the group we're adding on, what are we going to do next? Well, I'm going to just treat this as if the chlorine popped off. I realize that's not exactly what happened for the reasons I showed you earlier when I worked out the full mechanism, but this is really useful for figuring out what the product is going to look like. So, by simplifying things and treating the chlorine as if it pops off, we're left with the secondary carbocation. Can we rearrange? Of course. What's better than a secondary? A tertiary. So, seeing this hydrogen here next door, we're going to have a hydride shift, making our tertiary carbocation instead. All right, now what happens? Benzene's going to open up, and it can open up, since we're adding ortho and para, it can add in two different places, and it's going to reach and grab that positive site. And after elimination, we're going to end up with our two products, our ortho product and our para product. And that's all you have to do to get the right answer. I hope you enjoyed this episode of chemistry. We'll see you next time, and good luck.